Hello everybody, welcome to this new Pix4D webinar. My name is Oliver Kung, I'm one of the co-founders of Pix4D, and today's topic is about how to get the best out of your 3D robotic platform for mapping and 3D modeling. I'm presenting today this webinar with my X8 mapping platform. This is the 3D robotic copter that's specialized for mapping and 3D modeling, as it comes with a nice camera there integrated in the drone, and also together with a copy of Pix4D Mapper to let you really perform mapping the best way. So in today's webinar, we're going to cover many different topics. At first, we're going to start with going step by step, which are the things you need to do before going outside and do the map, then how to really acquire the map, the images using the drone, and then coming back to the office, how to put the images in Pix4D Mapper, start the processing, and how to generate automosaic, point cloud, and elevation models. After this step by step, which will go quite quickly, we will then go in a few different selected topics, which are going to give a bit more direction on where to look further for mapping. The first thing is, first we're going to discuss about the difference between Pix4D Mapper LT that comes together with the drone and Pix4D Mapper Pro that has much more enhanced functionalities especially for 3D mapping. Then we'll talk about the difference between simple stitching and automosaic. What are the advantages, but also the limitation in doing one way or the others. The importance of flight plan. What are the things to take care of when you perform a flight plan, when you actually select the flight plan, what's important to get really good results. What to expect in terms of georeference when you are using either the GPS from the camera, the GPS from the drone, or the GCP that you would measure with other tools. How to perform quality control. Very often the results obtained are very pretty, but to go into to make sure that they are really accurate, there's another step to be done, and it's not because it looks pretty that actually it's really accurate. So we are going to explain how to make sure that it looks pretty and accurate. And finally, we'll go into more advanced usage of the whole mapping platform, such as distances, volumetric measurements, contour lines, and many more usage of this platform. So let's get started. This is a little bit of the summary of the things to check before flights, to do during the flights, and then how to start the software and the processing. So before mission, the most important is to first check the 3D robotic flight instruction that came together with the drone, and to make sure to follow up all the safety instruction about the camera, the propellers, and the battery. Something we recommend in addition is to make sure that the camera is powered on, it has sufficient disk space, and you can go into the menu of the camera and disable the GPS function. As we will explain later, the GPS of the camera is not sufficient for accurate mapping. However, your drone is coming with the built-in GPS, and there's a way to extract the log file to use it for geotagging the images, which we are going to show just after that. So you can safely disable the camera GPS function of your camera, and this way you will save battery time and also make sure that you don't take this wrong GPS into account. You can also, depending on the day, the luminosity which is outside, you can adjust the exposure settings to make sure that you don't have overexposed or underexposed area in the images. Once you have made sure that all of this is done, you can then start planning the mission using mission control software. Here is Mission Planner 1.3. In Mission Planner 1.3, you can first need to go on Flight Plan, go in the region of interest. So Pix4D is located in Switzerland, right in this area. This is our office right there. And you have two choices to make a survey grid. However, in the current state of Mission Planner 1.3, we do not recommend to use Survey Grid version 2, and we would really recommend to use Survey Grid version 1. To use the Survey Grid, the first thing you need to do is you need to draw a polygon. By clicking a few times, you can define the zone in which you want to do your flight. You can refine a little bit the area. Let's do something like this. And then you need to select Auto WP, Survey Grid, and don't choose Grid version 2, only choose Grid version 1. This opens a new window. In this window, you have to choose here the camera type. In our case, we have a Canon SX280. And as well, I would recommend to check the Advanced option button there. If you click the Advanced option, you see that there you have two additional tab menu that you can choose. The first one is the most important one. And we really advise to change the default value of 50/50 to a values of 80 and 70. This is what controls the overlap of each pictures. And for the whole technology, for the whole maps to be of good quality, we really recommend to use very large values of something like 80/70. In addition, Mission Planner is not exactly following what you tell it to do it there. So even if you write 80 and 70, you will most likely have values around 60 and 70. So make sure that 80 and 70 are there. Once this is done, whoops, I just forgot to go there. So Survey Grid 70. Grid option 80/70, you go back in Simple and press Accept. My home altitude, okay. And now this is now a flight plan for mapping. Once you need to turn on your copter platform and press on Write WP. This will send the waypoints that you just computed there inside of the copter. You can then now go in the field with your copter, start a mission as indicated in the 3DRobotic procedure, and the drone's going to automatically go over the mission and take the pictures with sufficient overlap. Once the mission is done, basically you've got to take the camera out of the drone, to take the SD card, and to plug the SD card into your computer and download the imagery. In addition, you also have to take your copter, to plug a USB cable in this plug it to your computer, open Mission Planner, go into Flight Data, then you have the data, the logs, and download the logs to your computer. This will create a log file which is very precious because this log file contains the GPS tags for all of your imagery. So make sure that you download it. Once this tag and the images are downloaded on your computer, you can then so this would be the images of my mission. You can visualize one by one. And there you can see the log file of my flight, which is this log file there. So then the only thing you have to do is to start a new instance of Pix4D Mapper. Okay, here's a Pix4D Mapper, LT 3D Robotic Edition. You can create a new project. Okay, the project will be 3DR test 1, 2. Next, then you simply need to copy paste, to drag and drop the images into this box. Next. Then you use from file 3D robotic flight log, and you select the log file that I just mentioned before. And this is now writing the correct geotag inside of the images. Once this is done, you can press next, finish. And now you can see the mission that I just did over our office using the 3DR platform. The only thing you have to do left is click on Start, and this will start the processing and run the alignment of the imagery, the 3D modeling, and out of the 3D modeling, the extraction of auto mosaic. To process such a dataset, which is a pretty small dataset, it would take a couple of dozens of minutes. So something like for the whole imagery, the whole auto mosaic, elevation, 3D model, something like between half an hour and an hour of processing on a laptop. So I'm not going to do it. I will show some project that we already, the same project that we already processed. So if we skip this part, after processing, this is what we would obtain. So you see the position, the camera position that the software was able to compute, as well as the 3D model that it generated below. This is a cloud of points. And this generated also a mosaic, an auto mosaic of the whole surrounding around it. All right, this is concluding the easy step-by-step, showing really which are the steps you need to follow to go from preparing a mission, flying the drones, and then using the images to process to get some results. Now let's go in a few selected topics to get better understanding of what happened there, what's possible to do, and what should you do also when for certain type of results. So the first thing to talk about is the difference between Pix4D Mapper LT and Pix4D Mapper Pro. Pix4D Mapper LT, which is here on the right, is very, very similar to Pix4D Mapper Pro, which is here on the left. The main difference between the two software is the fact that the LT version is limited of generating auto mosaic. If you need to generate measurements in 2D and 3D, volumetric measurements, point clouds, meshes, 3D models, and to use advanced tools such as the mosaic editor and the index calculator, then you will need to upgrade to Pix4D Mapper Pro. However, Pix4D Mapper LT is able to generate perfect auto mosaic and to use still most of the tools for accurate georeferencement. Now let's go into the subject about what's the difference between stitching and auto mosaic. Stitching is what usually people say when they have a bunch of images and the goal is to put them together to make a coherent map. But the thing is, it's not that easy as what it looks like. For example, let's look at these two images taken from the dataset I just did earlier. If you look at these two images, it represents the same area, and possibly it should be able to stitch them together to get a full map. So one way to do it is to take the two images and try to position, maybe rotate and scale them a little bit until they fit together. And by playing a bit, this is the best I managed to do by trying to fit them together. But that's not exactly right. There are some things which do not work that way by doing this way. Actually, what we'd love to have is not a mosaic of images put together. It's much more something that you can see on the right, where you see that you have a top view, a perfect top view of the imagery without any facade, side of buildings, and any distortion. And when you look at it even more closely, what are the differences between this on the left, which is a steeple stitch, and on the right, which is actually an auto mosaic? On the left, you've got, as I just mentioned before, you've got the facade of the building, which should not happen to appear in a map. You have some issues of misalignment between the images. And you also have that if you try to measure the distance here of the roof, it's actually not the correct distance. It's a wrong measurement if you do it in this simple stitch that versus if you do it in the auto mosaic. And the reason for it is pretty simple. It is perspective. So the camera, and actually most of the camera and all of the camera which are consumer camera are cameras that are affected by perspective. And perspective is the fact that objects which are close to the camera look very, very big, and objects which are very far away look very small, right? This is the same that when your eye, which is also a perspective camera, you have your finger in front, it looks like a very big finger, and when you put your finger further away, it looks very small. So this is the effect of perspective. And when you take your pictures, you have this effect of perspective. And the closer you are to the object, the more perspective you have. And this is the perspective which makes it not possible to measure objects in normal imagery. Because the size of the roof, since it's closer to the camera than the ground, it's actually going to look bigger than what it is in reality. And to go from what we have there on the left to the right, you actually have to go through a process that's going to remove perspective or cancel perspective. And this process of removing perspective is called auto-rectification. And once you have auto-rectified a perspective set of images, you obtain an auto-mosaic. And that's really what an auto-mosaic is about. It's about having a map in which every distance are correct and preserved, meaning that you can measure everything correctly there, and also in which you only have the top viewing part of the image. So in this auto mosaic that was generated in Pix4D Mapper using this set of images, you don't see the facade anymore. You don't see the facade down there anymore either. You only really see as if it was a satellite taking the imagery from very high above. And this is what Pix4D Mapper allows you to do. It allows you to go from a set of images into a very accurate auto mosaic. But to do so, it has to go through many different steps, and that's what we're going to see now. What I'm going to explain there could be explained in the length of many different other webinars, and by the way, there are many other webinars that we did previously which are exactly in this topic, but I'm just going to summarize the different steps to understand through what the software has to go from simple images into an automosaic. So the first affirmation is that simple stitching does not work for UAV imagery, as the 3D model is required to generate an automosaic. So to rectify, to go from the left to the right, what you actually need is to understand the whole 3D geometry to be able to remove the facade. Only once you know that it's a facade looking from the side, you can actually do the mathematics to remove it and obtain such an imagery. And for that, you require a very precise 3D model of the terrain. And this is what the first sentence there. Stitching does not work because of perspective, and if you want to auto-rectify the image, you need a 3D model. Good. But then how do you get this 3D model? And that's what the second sentence there says. If you have two calibrated cameras, you can recover 3D information and generate 3D models. Okay? So if you take images and you have at least two images, but usually in a flight you will have hundreds of them, there is a way to mathematically do stereoscopy in software and recover the 3D information out of that. However, for that you need something that I just called calibrated camera. Calibrated cameras are cameras for which you know the exact position, orientation, and also how internally the perspective is working in it. However, the good news is that if you have sufficient overlap between the images, then it is possible to do some image correspondences between the images and something that we call key points and key points matching. And if you have enough key points to do key point matching, then there is a possibility to do automatic self-calibration, meaning that you can turn a set of camera into a calibrated set of camera, and from this calibrated set of camera you can make a 3D model. And if you have then this calibrated cameras making a 3D model, you can then use this 3D model and the cameras to generate an auto-rectified mosaic, an automosaic. So now that's a more graphic view of what I just said. So in the chronological order, you have all your imagery, hundreds of images. In each images, you will find interesting area, something we call key points. Usually you will find 10,000 of them for each image. So this is what the software is doing automatically. And then it's going to match across all the imagery, these key points for each image together. So in this graphic I only show two images, but the software is performing this with hundreds or thousands of imagery. Once this is done, it's able to do what we call calibration. Calibration meaning trying to recompute what was the original position of each imagery. From this calibration, it's able then to compute a 3D point cloud. A 3D point cloud is a lot of little points in 3D space which are computed from the imagery. From this 3D point cloud, it's possible then to generate an elevation model. This is what we call a DSM, digital surface model, where you can really map for every part of the scene what is the current altitude. And from this elevation model, it is then possible to rectify the perspective effects and to generate an automosaic. And all these steps is what Pix4D Mapper is doing when you click start in the processing, and you wait and you get an automosaic at the end. Again, if you want to have more information about this whole process, there is a whole dedicated webinar in the support knowledge base of Pix4D Mapper of Pix4D, which is dedicated to this topic. But that should give quite a nice overview of what's happening behind the scene when you click on the start button. So this whole process depends on many things, and one of the most important things it depends to ensure the best quality, as I mentioned in the very beginning, is a proper flight plan. And what does a good flight plan means? Basically, for mapping, a good flight plan is a flight plan with a lot of overlap, a lot of redundancy between the images, and a very nice spacing of these images. So if you have tons of images in one spot and nothing in the other area, it's not very useful. You need to have it really, really spread across the whole scene you're going to map. This is essential, really essential. And just to give you an idea of how essential it is, you probably are going to get much better results if you have proper overlap with a medium camera than if you try to do mapping with little overlap with a very, very heavy and expensive and good quality camera. So it's more important, the overlap, than almost the quality of the camera. So if you have a better camera, you always will get better results, but not that much compared to the importance of proper overlap. So as I just said before, you don't want to have a low overlap. If you have low overlap, then the whole process I just explained before of key point matching will not work well, because if your images have 10% of overlap, there'll be almost no content to match between the two images. And you really need something more in the range of 60 or 80% of overlap. Not only it's not sufficient, but in addition, if you have little overlap, you may have something which is what we call error accumulation, which is happening. This is very hard to detect, but when this is happening, you may start to have the model drifting, and even it's very hard to detect from a visual point of view, you may end up with difference of altitude of several meters at the end of your project without seeing it. And this is what happens when your overlap is not sufficient. However, that's just to do it on the other side. If your overlap is too high and your images are too close, this has an effect which we call the short baseline effect. Short baseline means that if your images are very, very close by, then the 3D cannot be computed accurately, and the error that you produce by having images too close is actually making more error in your project than if you didn't have this image. In addition, it also makes slower computation, and then you also have the risk of error accumulation. So you really need an overlap which is in the range that we discussed there. So as I described in the flight mission planner before, there I put the value of 70 and 80, which is something very reasonable. Now, not only does the overlap has an effect, it's not just the overlap, so the distance between imagery that's always a constant. It depends a lot on your terrain of what are you trying to map. To give an example, if you have objects of different heights in your scene that you're trying to map, then if you would keep the same distance between every shot, if you're on the ground, good. Let's pretend you have 70 overlap. Now let's imagine that you have a building in your scene. Then actually your camera is going to stop at the roof, on the roof of the building. You're going to take a picture of the roof of the building. But because it's much closer to the camera, even with the same distance between the images, you will get potentially an overlap on only 40%. And if your building is even higher, you may even end up in the state where you have 0% overlap on the top of the building. And there nothing is possible. So that's just an example to show that the overlap depends on the distance to the object, and it's easy to make mistakes there. So what should you do in this type of situation when you have buildings in the place you try to map? Well, you should set the overlap in Mission Planner with respect to the closest object to the camera and not to the furthest one. So either you would fly a few more meters more in altitude, or you have to increase even more the overlap in your scene. So for this example, either you would fly much higher, let's say 10-20 meters higher for this one, and then you will have again some overlap here, or you have to decrease the distance between the shots. And that allows me to go back to Mission Planner. So again, as I mentioned earlier, use AutoWP Survey Grid and do not use version 2, version 2, sorry. The reason for that is that version 2 has an issue that the overlap by default is too low, and it's not possible to override the overlap settings. So that's the big reason. If you try to do a survey with the version 2, you will have not sufficient overlap, and the project will mostly fail or will contain large errors in it. So really use version 1 and set the numbers at 70-80 or 70-70. And also remember that even if you put 70-70 as numbers there, you will probably obtain the UAV is going to fly with a little less overlap, because Mission Planner is a bit overestimating or underestimating the values. Okay, now another of this selected topic is about georeference. So georeference is about where does the automosaic fit inside of what are the coordinates of this map. And georeferencement is really about how is it positioned, your automosaic, and also the scale and the orientation of it. So there are three possibilities. Actually four possibilities. Either you fly and you process imagery without any GPS. We do not recommend not to input any GPS when starting the processing for a few reasons. So the software is going to work, right? The software does not require GPS, but we do not recommend it because it's going to be slower to process. You have more likelihood that it fails during the processing. Plus, at the end, your automosaic will have no scale, position, and orientation. So from images only without any GPS information, it is not possible to compute. We don't know if the project is 1 centimeter large or 20 kilometer large. And the software will estimate some value, but they will be very, very wrong. So you do not rely on that if you don't have GPS. However, if you have a few GCP, so ground control points, meaning measurement you did using another device in the scene, then it is possible to perfectly fix the scale, the position, and the orientation. But since your 3D robotic platforms comes with a good GPS inside, it would be really a pity not to use it. So the other way you can use is the GPS of the camera. As I mentioned in the very beginning of this webinar, I really recommend not to use it. The GPS of the camera has a refresh rate which is really way too slow, and the accuracy you obtain is something in the range of 20 meters per picture. And actually you are adding more mistakes to you're confusing the software by adding such irrelevant data than actually helping it. So by default, don't use the GPS of the camera. And if you disable it, as I showed in the beginning, you can even save battery of your camera. However, something to be really nice, that's really nice to use, is the GPS of the flight log. So as I mentioned, you can, after the flight, connect the drone to your computer, get the flight log of the mission, and then you can import this log file into Pix4D Mapper to use it to really tag the imagery. And tagging this imagery is really the recommended workflow, as it's faster to process, it's much more likely to work very well. In addition, you have some quality, it can be used for quality control. Finally, you can use ground control point in addition of using the GPS of the flight log. And this is the only way to achieve absolute accuracy. So before talking further, let's just use this summary table. If you don't have a GPS, you will have a bad scale estimation, bad orientation estimation, no position estimation. And really we don't recommend to process without any GPS information. If you use the flight log GPS, you will have a pretty good scale estimation, a pretty good orientation estimation, and a medium position estimation. Medium, why? Basically, the GPS which comes inside of the drone is very accurate relatively. It's accurate for something like around 1 meter that you can see, as you can see in the project there. So here are the GPS points, and you can see that they are really nicely following the path, which give a good indication that they are very accurate, something like a meter. However, due to the atmospheric condition of the Earth, you actually have all these points are very likely shifted of a few meters in a random direction. This is just because of how GPS, consumer grade GPS, is working. And you should not expect a positioning of your image, of your final automosaic, better than something like 5 meters in X, Y, or Z. So you'll have a small offset there. If you want to correct this, the only way to do it is to use a professional GPS that is used by surveyors. Just to give an idea, this type of GPS is in the range starting at $8,000. And these are the surveyor equipments which they are using in the fields with kind of it's a stick with a GPS on it that you can use to measure points on the ground. So there the goal using ground control points is before doing the flights, you would go in the scene, you would mark a few points on the ground using maybe a spray, a red spray on the ground to make a big cross. You would then take your GPS, your professional grade GPS, and measure up to centimeter accuracy the position at that point. You would write this down on a log file, and then you would do the flight, do the processing, and then there's a way in Pix4D Mapper to import this position, to import these ground control points and mark them in the images to be able to get an absolute positioning of the project. There is a whole webinar dedicated to this subject, so for people using ground control points, I really recommend to you to watch the whole ground control points webinar. And if you do that, then you really have perfect scale, perfect orientation, position estimation. Just to give a hint in terms, as we still talk about accuracy and georeference, the accuracy that you should expect of the whole processing if you use ground control points is about 3 pixel, is an accuracy of 3 pixel. So if a pixel is 2 centimeters on the ground, then you can expect an accuracy of your whole project to be within 6 centimeters, something like that. So 3 times the pixel size, if everything is done correctly. And accuracy leads me also to start into quality control. So quality control is really the fact that it's not because it looks pretty that it's accurate. And when you need really to go into the accuracy, you need to check many things to be really sure that the whole project is actually good. The first thing which is there is the quality report. The quality report is the report that pops in just after the first step of calibration, of processing. It has many information about how did the whole processing went and so on. But the first thing that you will need to check is this rapid quality check green checks there. Basically, if everything is green, it means that there's a high likelihood that your project really went well and that it's pretty accurate and there hasn't been any issue. As a tip, most of the time when this turns yellow or red, it's 90% of the time because the flight plan was not adapted and there was not sufficient overlap for this project. So first thing to check all the time is make sure that you have enough imagery for your project. You can see that this one is orange, the last one is orange. It's because there has been no ground control points in this project, and without ground control points, it's impossible to say how good the quality of the georeferencement is. So we're just saying it's in orange to let the user know that the software cannot give an advice on how good the georeferencement is. Another very interesting graph is to check the overlap graph. In this project, you can see that it's not always green. It's a bit orange and red. And to have a really good project, you should always have everything green. Now, if you look a little bit at the specific data set I just did there, the orange part is happening where you have buildings. And this is exactly what I mentioned just before. If you have buildings in your data set, then there will be less overlap on top of them. And in Mission Planner, I should have chosen even higher overlap to my mission to make sure that I would have also consistent overlap on top of my building. So when I see this type of graph, this gives me a good insight that next time I do a mapping of this area, I should even make my overlap settings a bit higher, or I should also fly a bit higher. I was too close to the ground, which makes it more complicated. The quality report gives you a lot of hints that you can click, basically all the hints to if things turns orange or have issues. You have help, integrated help that lets you know what to do and how to improve the results. But again, most of the time issues come when you don't have sufficient overlap. So make sure that you have decent overlap. Another way to do quality check, quality control, is to use the ray cloud. In Pix4D Mapper, you have this interface that we call the ray cloud, which is what you see there. And it's much more than a simple 3D viewer. It's really what makes the connection between the 3D that you computed and the imagery that you took. One way to do quality check in the ray cloud is to click on any point and to validate on the view on the right that this point indeed reprojects, so that the green cross is indeed exactly on the same location of every image. If you see some issue that a point starts to behave not to reproject on every image, this is a very good indication that maybe there is issue in the processing, and that you need to follow the steps to improve the process. Another way also is to select an image and to see the distribution of the key point over the image. If the goal is always that the key points are as well distributed on the image as possible and not to miss some parts. Again, this is quite an advanced topic and there's a lot of of webinars dedicated to this exact question. I would still mention that for the most advanced accuracy control, still the only way to do it properly now is to use ground control points. So in this mission, if someone really wanted to be sure of the accuracy of the whole project, you would basically have to take a few measurements on the ground and to import them in Pix4D Mapper and to compare the accuracy at this point versus what the software gave. And this can give you a good indication. I'm also going to quickly show how to improve things when it went wrong. There's the possibility in Pix4D Mapper to add manual tie points, which is one of the best way to improve accuracy in a project. So for example, if I see that one of my 3D points is not accurately reprojected on each, you can create a manual tie point, interact with the imagery, and with the click I just did, you can basically you will improve the accuracy in this area, as well as visualize the type of error which is happening in this area and how to improve it. Okay, so by adding some more manual work in it, you're able to control very precisely at certain areas the accuracy of your project, and by doing so you're basically able to improve the accuracy there. But again, this is an advanced topic, which is I would really recommend to watch the whole webinar about ground control points about it. Okay, now I'll quickly go over also the more advanced features of Pix4D Mapper, what's possible to do with it in addition of what I just showed there, and also to discuss a little bit about the results of my project. Okay, so here you can see in the Ray Cloud, which is really the best tool to understand what's happening in your project. You can see in blue, this is what the drone recorded as a GPS position, and in green it's what the software computed. So the software from pixel matching is able to be much more precise than whatever the GPS gives you, and can give you really centimeter accuracy in the positioning of the images, and that's where you can see the difference. You can also see a slight difference between the green and the blue. This is because of the synchronization between the camera and the GPS readout time. But this is nothing to worry about. This is a very good result. What's very interesting to see is this at some spots in the facade of the building, there is no point computed. However, there are imagery showing the facade of the building. But what you can see is that there is not enough imagery showing the facade of the building. Because the image was taken very, very nadir, pointing to the ground, and the overlap was not very high, there is not enough overlapping imagery to show the side of the building. So if my mission had a bit more overlap, or if the camera would have been tilted slightly oblique, then you would have full 3D computed also on the facade of the building. Another thing you can see in this dataset is the road here is not of very good quality and it's missing some points. The reason for it is if you click on it, you can see the imagery. And what you can see in the imagery is that the road was very reflective and was overexposed, meaning there was no information about pixels in this area. And because there's no information, this confuses the software and it's not able to compute precisely 3D information in it. So to avoid that, as I mentioned earlier at the beginning of the webinar, one of the ways to do it would be to take the camera and to reduce the exposure time if you know that it's a very reflective and very bright environment. It's always better to be slightly underexposed than overexposed. You have more information. And this way you would have perfect information also on this reflective road. Okay, there are many things you can do in the Ray Cloud editor. One of them is you can perform volumetric measurements. So if you wanted to know the volume of this small houses which are right there, you can use the tool of Pix4D Mapper to basically select the volumetric measurement tool. Wait for the software to load. And then click around the place where you want to perform your volumetric measurement. Okay, so once you have this, then you have on the right shown in the properties what is the volume that just was computed there. You can do the same for distances. So the distance of this parking lot from here to here, and you can measure it of being 32 meters. You can also adjust these measurements to measure much more complicated things. For example, here I can see that there's a shadow of a lamppost, but the lamppost was too small to be reconstructed in 3D. However, thanks to the interface in Pix4D Mapper, you are able to go much further than what's normally possible with imagery. So, for example, I can see that here is the lamppost. So by moving the vertices from the bottom to the top and doing this in at least 2 imagery, you're basically able to measure the distance of an object which is not in which hasn't been computed in 3D, and you can measure that this lamppost is actually 10 meter altitude, and you can see how well it projects in every images. So this way you can go much further in what's able to extract as measurements from the imagery by themselves. You're of course able also to edit the point cloud when you need to delete some artifacts or some issues, by basically selecting any part of the building there and removing them for the point cloud. Remember, this point cloud is what is used to generate the DSM, which is in turn used to generate the automosaic. So by editing and improving the point cloud, it will generate a better DSM, and a better DSM will make an automosaic of better quality. A very interesting tool also, now talking about automosaic, is the tool which is also included, which give you the freedom to improve the automosaic and to do some changes. So inside of Pix4D Mapper, you can see here, this is the mosaic editing tool, and here you can see that there was a car moving while we took the pictures. So the same car is visible in these 2 images. But thanks to the tool, you can select which part of which image is reprojected into the final automosaic. So by choosing a better part of the image, you can basically make sure that moving objects are well removed and consistently removed. And you also control the brightness of different parts of the mosaic. And select which is the most appropriate image for this area. You also have the index calculator tool, but this is mostly used for farming purposes if you have multi-band imagery where you can compute formulas such as NDVI, but that's also a very different topic. You also have plenty of options in the menus to generate 3D PDFs, contour lines, meshes, and so on, but there's plenty of documentation on Pix4D Mapper website on how to achieve that. So with this, I did a good round of what is possible to do with 3D robotic platform and Pix4D Mapper software. So I hope you enjoyed the webinar. It gave you the good direction to start doing mapping properly and also accurately. And I hope you have a lot of enjoyment into flying the platform and using the software. And I thank you very much for listening to this webinar. And I hope you have a good day. And I hope to see you for the next one. All right. Goodbye, everybody. Thank you very much for listening to me. See you next time.